So what I want really when you leave the class tonight is to be able to look at your house, look at the parcel that the house is on, and think of things you can do both to the vegetation management part, but just sort of generically, but more importantly, to be able to look at the various components of your house and understand how we talk about fire-resistant materials and things about design that might make your house more or less vulnerable to wildfire, and things you can do to your house in terms of design, in terms of material changes that would be most beneficial in improving the chance of your home surviving a wildfire. Before we get into the specifics of materials, I thought we would just talk for a little bit about how we talk about the performance of materials from a fire perspective. How well do things burn? So these are some words that that people banter about. A material can be combustible. A material can be non-combustible. A material might be non-flammable. A material might be called fire resistant, ignition resistant, and with ignition resistant we have ignition resistant material and ignition resistant construction. Are those the same thing? And then this flame resistant. What else have you heard in terms of describing the performance of a material to fire? Are there any other terms?
Fire retardant.
Fire retardant material. Fireproof material. What do these things mean? So some of these, you'll notice, are highlighted in red. And the ones that are in red, there are definite definitions for these things, for these terms. The other ones, non-flammable, you might say, well, that's the same as non-combustible. But is it really? Because actually the definition of non-combustible allows some flaming. So maybe not. And then flame resistant, well, you sort of understand what that means, but when you look at multiple materials, how do you know what attribute to give to a given material? So we're going to talk about these a little bit. Okay, so here's a question for you. Fire resistant and ignition resistant mean the same thing. False. Fire resistant and ignition resistant mean the same thing. So we'll talk more in detail about this, but fire resistant and ignition resistant don't mean the same thing. They're different. Is something that is fire resistant better than something that's ignition resistant? Maybe. We will look into these things in the next couple of slides. So this is a horizontal tunnel where there's a gas flame at the beginning of it, and the material that's being tested is along the top of the tunnel, so the fire is underneath it. This is called a Steiner Tunnel, and it's a piece of equipment that is used to evaluate flame spread. How many of you heard Class A flame spread? Heard that term. This is where it comes from. A Class A flame spread means that the flame doesn't travel down the tunnel but so far, and if you go to the end of the tunnel, then you have a flame spread that is not as good as one that doesn't go very far at all. So this is how you get the flame spread rating. This is also the test that is used to determine whether or not in California, and other people are picking it up, they've just defined ignition resistant as also something that is developed in this tunnel. So something that is ignition resistant has performed in a certain way in this tunnel, and something that is Class A has also performed in a certain way in this tunnel. So let's look to the next slide. This is what it looks like on the inside. It's not so big, and the material that's being tested is in the top, and then the gas burners are right there, and you track the progress of the flame as it goes down the tunnel. When it reaches a certain point, then it stops, or when the test ends, and you mark that, and you calculate what the flame spread would be. Class A, Class B, Class C are commonly used terms. This is a way to evaluate sort of the combustibility of combustible materials, and it is used to get to whether or not a material can be considered ignition resistant or not. Okay, so flame spread rating, class A, B, or C are common, and then in California and to some building code definitions, ignition-resistant material is also determined using this tunnel. Okay, so this is a commercial fire lab up in Washington State, a picture of, and this is a big hood. When something underneath this hood is ignited, this is an exhaust hood. The fumes go up. You measure gases coming off of the thing that's burning, and you can calculate the energy released while it burns. So this isn't anything that's you can define anything by, but it is a way to compare performance of things that are combustible. So if the energy release, heat release rate is 1,000, comparing to a material that has a heat release rate of 500, then you know that the 1,001 burns better than the 500 one. Okay, and then if you have a tiny thing, a tinier thing, under this hood, this is for a larger. You can put like components. You can put outside. You can have a large deck underneath this hood. If you have a piece of that deck or a piece of the siding, then you can measure the same thing, the same heat release rate, in this thing called a cone calorimeter. So here's the cone, and then you put the material here, and you heat up the thing that you're testing. It'll ignite, and you can measure the energy that is released when it burns. And so if you look up into it, this is the cone, and this is the heating element. It's called a cone because it's shaped like a cone. So a cone calorimeter, you get the same heat release rate information, but you do it on smaller things. So combustible materials, the way that you can use to evaluate how well a combustible material burns or how vigorously it'll burn, you can compare flame spread ratings, class A, B, or C, and you can compare heat release rate information, should it be available. It's really easy to find flame spread information for various combustible materials, so you can choose that way. And you can ask for heat release information. Okay, so fire resistant. So that was a term. Fire resistant is a term that's used most often for interior fires, and it's a way to describe how easily fire can move from one room to another. It's used commonly in apartment or condominium or townhouses where you want to stop fire from one unit from going into another unit, and this rating is often called a 1 hour rating or a 2 hour rating. So it's just it's not really 1 hour resistance, but it's just a nominal rating that provides a relative comparison of how well a given construction resists the fire moving from room A to room B, or attic space A to attic space B. And typically you do this using specialized gypsum wallboard. So in this particular example here, we have gypsum wallboard on the exterior of this unit and also on the exterior of this unit. So together, there's two pieces of gyp right together. So this is a fire-resistant rating, and in order to get that, you have this big vertical furnace, and you put the wall in, you run a particular time temperature curve. So there's a temperature inside of this furnace, and you look to see whether fire will come through the wall into what would be the outside world or not. So in a 1 hour test, you're going to reach a temperature of about 1,700 degrees Fahrenheit. It's pretty hot. So this is how you get a fire-resistant rating on a wall. Excuse me. You can do it same thing for a door, same thing for a window. And then there's a horizontal one of these furnaces for a floor system. So you can get fire-resistant ratings for movement vertically and movement horizontally in a structure. And you get this X minute, that's the way you read these as X minutes or X hour rating. So for a door or window, you might have a 20-minute door or window. And for a wall or a floor, you can have a 1 or 2 hour or common terms. So this doesn't apply directly to wildfire situations, but many people are adopting 1 hour wall construction for exterior walls for wildfire situations. So if you have so-called one-hour wall construction for your house. You would have the siding on the outside, and then somewhere between the siding and your stud wall, you're going to have gypsum wallboard in that assembly. So even though it doesn't apply directly, it is used in defining acceptable products or assemblies for wildfire exposures. This is a particular kind of furnace that is used to determine whether or not a material can be considered non-combustible or not. So there are certain things that you sort of know, you feel in your head it's non-combustible, like lightweight concrete. You might think, well, that's non-combustible. Stucco, you might think, well, that's non-combustible. But fiber cement, people think it's non-combustible, but the fiber in fiber cement is a wood fiber. So really, it's sort of a function of how much is in there, maybe. And so they, for example, would use this test to confirm that they're non-combustible or not. The definition says, you might think the definition is a material that isn't capable of igniting or burning. Sound about right for non-combustible? Actually, the definition says that you can have a limited amount of flaming, a limited amount of weight loss, and so as long as you meet the definition, you can be considered non-combustible. So another kind of fire-resistant rating would be that used in roof coverings. So this is what you can see here is a test of a roof section that is used to get the Class A, B, or C roof rating. So Class A, B, or C roof rating is not the same thing as a Class A, B, or C flame spread. They use the same terms, but they refer to different things. So when you're talking about a roof and you hear Class A, then it's this test. When you're talking about almost any other kind of material and you hear Class A, it's a flame spread kind of a rating. There are 3 parts to a roof test. The one that we're looking at here is the brand test. And what we see in this particular test is this Class A brand. And it's a 12 inches by 12 inch piece of material. And as you can see, it is a sandwich construction. And it's 3/4 inch square Douglas fir sticks that are nailed together. The inside, the middle layer of the sandwich is perpendicular to the outer layers. So you have a lot of holes in it. It's porous. You ignite this, you put it on the deck, and you wait to see whether by the time this burns out or by the time the burning activity on the roof stops, you don't have fire penetrating through the deck into what would be the attic. If you have fire penetrating through the deck into what would be the attic, then you don't have the Class whatever roof. So this is the Class A. This is a Class B. Somewhere in transit, the Class C went missing, but the Class C brand is about the shape of an ice cube. It's pretty small. You're going to put 20 of them on the roof, but it's still a lot smaller than the A or the B. So this is the Class ABC test. There are 3 parts of this test. Class A, the first part is this penetration test, which is like the fire resistant test. It's how well can it resist fire penetrating into the roof, into the attic. Part 2 would be a flame spread test over the roof covering, and part 3 would be whether or not the roof covering generates embers or not. 3 parts. You have to meet all 3 to be Class A, or B or C. You need to meet certain requirements for Class A, certain requirements for Class B and C, all 3 parts. This is another example of a assembly-rated roof. In this case, it is a pressure-impregnated, fire-retardant treated wood shake. So this is untreated. This isn't even a Class C rated roof. Treated like this, it's a Class B by itself. By assembly, it's a Class A if you have some underlying material. So this is an example of such a material. This is something called Densdeck. It's a gypsum fiberglass product. And when you have the assembly like this, and you can put the Class A on top of it, and it'll pass the test. Similarly, you can put this roll roofing on, and it'll also pass the test. So you're good. You can go either way. So this is an aluminum roof, a picture of an aluminum roof being tested. And this is one reason why aluminum roofing isn't really lumped into the same category as steel. Because of the relatively low melting point, the Class A brand, in this case, sits mostly on the thing underneath the roof. And what we're seeing here is the Class A brand sitting on top of this cap sheet material. And so in this construction, it'll pass, but without it, it won't, because of the fact that the Class A brand sitting on top of it will burn right through the covering. So another example of an assembly-rated roof covering. And we've talked about assembly rating in terms of the 1 hour construction where you have the gypsum in addition to everything else in that wall assembly. We'll see along that assembly ratings happen a lot, and they can be pretty important to how they work, and it's really important to follow the directions on things that have an assembly rating, because that's how they were tested, that's how they perform according to the way that you think they should be performing. So if you're using a roll roofing product, then you want to make sure you get a good look at the wrapping and make sure that it says something to the effect that it's rated for exterior fire exposure. These products are sold generically. There is a difference in performance if it doesn't have this rating on it. So when you park your car in a no parking zone, implications aren't so onerous, I suppose. But if you have an assembly rated product, then you need to install it that way, because the consequences go beyond a misparked car. It results in failure of the system. Okay, so we're going to sort of review this a little bit. Fire resistant ratings. They're the things that nominally are used to evaluate or to describe resistance to fire movement from one room to another room, from one space to another space. It is used in wildfire to define the resistance of fire moving from the outside in, but traditionally this has been a room, interior space to interior space. And you get this 20-minute or 1 or 2 hour rating for wall, floor, or other component. Non-combustible there's a test to describe whether it's non-combustible or not. Things that you have a question about, you should be able to ask the manufacturer. They should be able to tell you and show you test results about the non-combustibility test. It's a particular standard method, and it'll indicate non-combustibility via this test method. Ignition resistant material. So incorporated in this is it has to be weathered according to a certain standard and then pass the test, this flame spread test. So there's a particular way that this has to be tested, and if it passes, this is a go, no-go kind of test. It either is or it isn't. It either is non-ignition resistant material or not. And then combustible materials, well, you can use certain things to evaluate differences in combustibility, and you can use things like the heat release rate if you can find it. Easily findable is the flame spread rating of the material. So we've sort of talked about this. There are a number of products that comply to this new building code in California, and the State Fire Marshal's Office maintains a free download of products that have complied, and the link is in this upper portion of this slide. So here's another question. So the question is, all products listed in the Wildland Urban Interface Product Handbook are ignition-resistant materials. True or false? True or false, all products listed in the WUI Product Handbook are ignition-resistant materials. But actually, things in here are not all ignition-resistant. Certain things are, certain things aren't. The California Code is the ignition-resistant construction guide, so to speak, but it allows combustible materials. And so things in this have passed a test, but it isn't a non-combustibility test. It isn't necessarily an ignition-resistant material test. It is a test that evaluates a certain performance to a known fire exposure. So let's talk about some of the state tests that are tied to the building code. So there are tests for siding, there's tests for eave materials or soffit materials, there are tests for decking, testing for windows. I think that's it. So this is a test of the wall. You see it's a burning wall. What's this with the wall test, with the eave and soffit test, and what the window test, they all use the same basic apparatus that you see here in the wall test. In the eave, you're putting non-combustible things where the wall is. You're putting the eave material up here. In the wall, you're putting whatever you're testing in the wall, and everything else is non-combustible. In the window test, you put a window in the middle of that wall, and you expose it to a fire from a gas burner at the base of the wall. And what you're looking at in each one of these tests is whether or not, during the prescribed time, whether fire penetrates through the thing, the wall, the eave, the window, into what would be either the stud cavity or the living space. If it does penetrate into, then it doesn't pass. It can't be used. It won't comply. With a window, it can break the glass and get in, or it can burn through the frame and get in. Either way, the key is whether it gets into the living space of the structure. Okay, so these explicitly allow combustible things. It evaluates the resistance to penetration, so it's more or less a fire-resistant test. Okay, and here's the deck test. And this deck test it evaluates energy released while it burns. With the heat release rate is important. This one wouldn't pass, this test on the left. And it also wants to know whether the deck itself drops burning debris or not. Part of this test also is whether it'll put itself out in a prescribed amount of time, whether the material will put itself out after the fire exposure. And this deck is exposed to a flame from underneath for 3 minutes, and then you wait and see what happens. And you measure the energy released, and you make observations on whether things fall, and then you make observations into whether the deck self-extinguishes. So these things are tied to the state code. If you pass these tests, you can be put in this book. If you become an ignition-resistant material by passing that flame spread test, you can get yourself put in this book. And this also allows for assembly. So if you need to use gypsum wallboard, for example, to pass the test, then you need to be installed that way, but you can pass the test and be put in the book. So if you understand the limitations of this, then it'll help you, I think, in thinking about what kind of materials to get. So now let's just look at your home. Think about your home on your plot of land. There are the slope and whatnot around your house, and then there's your house itself. We're going to be focusing on the house itself, but if you are on level ground, then your exposure might be one kind of exposure. If you are on a slope without any setback, and the fire can come up the hill at you, you have overhanging deck, big eave, then you need to think about these particular components in particular, because they may need special treatment if you want to reinforce your house part, given how your house is set on the property. And similarly, if you're set back, then it would be less severe exposure potentially, but you still may have some vulnerable parts to your house. And similarly, the other option would be a downslope to a fire. It can be running downhill towards you. And this one might be more of an ember kind of exposure depending on your setback and your defensible space. So one thing that you can consider, we're not going to really go any further into this, but if you're on a slope, you can use hardscaping features like a retaining wall that might stop the fire, short of your building. So you might only need to be worried mostly about ember exposure instead of the fire coming all the way to the house. So I think it's pretty clear in my mind that the roof is the most important part of your house because it's the largest horizontal surface. It's ready for all comers in terms of embers and whatnot. It's vulnerable. So a Class A roof, in my mind, is where you want to be. But there are other things about your roof that you need to worry about. So this is something that I call a complex roof. And here you have a Class A roof covering, but you have things around that Class A roof. In this case, you have a roof-to-wall intersection on the roof. So, and what's the roof? Well, what's the siding? You can probably tell. It's wood wood shingle. So it's an untreated wood shingle siding. So you have, and what has accumulated in back of said shingle-clad wall? Leaves and such. And what else can accumulate there during a wildfire? Embers. Okay, so you have a Class A roof. You could feel safe, but because of this particular design, you shouldn't feel so safe. So if you have a house like this, you can feel good about the roof, but you need to do other things. And you could decide that you're just going to keep that roof clean all the time, or you could do something about the siding so that the roof, so that the siding gives you the same relative performance as a Class A roof does. So you could replace the siding. You could put in a non-combustible siding. You could put in something that meets the ignition-resistant material classification. You could replace that way. Replacing all the siding on your house could be expensive. You could locally replace. No one sees that side anyway, particularly. So you could replace locally something that's more fire safe in this particular case because of this particular design and the way that you have it there. So we're going to continue on the same vein by looking at edge of roof issues. Okay, so here we have clay barrel tile roof, which, maybe isn't the most important kind of roof you have up here, but it describes the point that you're going to be looking for. If you are open at the end of any kind of roof, so some metal roofs have little openings at the end. Clay barrel tile roofs definitely do. It's empty at the end. Debris can blow up under there. Birds can climb up into there, and rodents can climb up in there, build nests. There's a lot of fine fuels in nests. Embers will also flow up under there and ignite those fine fuels, which will then provide a flame contact exposure to larger structural members in that construction. This is a flat concrete tile roof. You can have gaps at the ridge also. So just because you don't see anything at the edge, an edge happens at the peak also. This is the close-up of the debris that has accumulated on this particular building in probably 15 years of use, where we took this off to waterproof this skylight, and this is what we saw. So there's a lot of debris that can accumulate over time. So what's the solution here? You guys have to come up with a solution. You don't have any gutters. What's another solution? So another solution could be gutter covers. Another, people are doing that. You could do a really good job of keeping debris cleaned out of your gutter. I don't even like that idea. I do have some examples of gutter covers. Thank you, Ed. There's a wire screen kind like this we're looking at that you slip underneath the edge of the roof. The water can come in. The idea is that the water comes in, debris doesn't, so the water gets into the gutter and out. And this is a combination solid screen type. So again, the upper part of the gutter cover slides underneath the roof. Water comes off the roof, and then goes into the gutter. Debris supposedly flows off. If you do a web search on gutter cover devices, you will find many. I have maybe 15 or 20 in a spreadsheet, and if you go to their website, every one of them is the best gutter cover known to man. So right now there isn't an independent way to evaluate performance. So you have to sort of think about how well you think it might work, remembering that many of them will allow for debris to accumulate in back of the roof, and then take appropriate steps. So vents. So we sort of talked about this a little bit, but this is a roof, and we see here at the base of the roof there are through roof vents that would be inlet vents, and then we have a ridge vent at the top here that would be the exiting or outlet air vent. Vents we have vents because they provide a moisture management function for the home. So enclosed spaces that are typically unconditioned are typically vented. So if you're built on a crawl space, you're going to have crawl space vents. If you're built, and you have an attic, you're going to have a vented space there. If you're a cathedral ceiling, you could have venting depending. So here's the idea that you have inlet and outlet in each space. So if you have a foundation or crawl space, you're going to have air coming in, air going out. Theoretically, the dry air comes in and more moist air goes out. From a fire perspective, vents have been shown not to be so good because they allow embers in, or firebrands in, and then they ignite fine fuels in the attic. And even so, how many of you store stuff in your attic? So I take it they would be combustible things like newspapers, magazines, or memorabilia, whatever, things like that. So even if you don't do that, a lot of debris can accumulate over time, just like in that under roof area that we saw. So this is some testing that we were doing, and here's an ember. This is a 1/8 of an inch mesh kind of vent. Here's a hot ember sitting on top of a 1/8 inch hole, and and it'll just, there's air blowing by it. So if in your case you could have an ember landing against the screen of your attic vent, and with air blowing on it, it'll just burn down. Assuming you have a screen, it'll burn down till it can fit through it and go through. Some testing that we've done and some testing that's been done at other labs have shown that depending on the combustibility of the fine fuel, how fine the fuel is, you can have fairly small embers igniting that fuel. And then the flame from that small fuel fire will then provide a flame contact exposure to the larger structural members in the attic, and you end up having an attic fire. So one thing is for sure, finer mesh screen is better, but finer mesh screen is easy to plug up. So here we have 1/8 of an inch mesh screen. Commonly these days, 1/4 inch mesh is pretty common. The code now allows 1/8 of an inch mesh. In California, the code will allow 1/16 of an inch mesh, next year. But here's 1/8 of an inch mesh screen, and you can maybe tell that there's a lot of debris that's plugged up these openings. This is a 1/16 of an inch mesh screen here, and it's been painted over. So if the screen weren't in such poor repair to the point where it's been torn out, it wouldn't have much air entry capability at all. So finer mesh means more maintenance for you. Finer mesh means smaller embers and less likelihood of ignition in the attic. for you also. So you can go that way. You can develop or pre-make vent covers if your vents are easily accessible. Put them on when wildfires are threatening. Take them off when they're not. So Ed asked whether you're going to still meet the ventilation code requirements if you use finer mesh screen. And this is one question that I anticipated, so I have some slides that we talk about that. So, but before we do that, there are, I think you can find them in the Tahoe Basin in particular. There are newer vents that have been designed and are now produced that have been designed to resist flame and ember entry. These are a lot more money than quarter-inch mesh screen, but here they are. The two that are the most common, I think, is one called Brand Guard that uses a baffle design, and another one called Vulcan, which uses a combination of screening and then an intumescent paint-coated honeycomb mesh. So both of these have been accepted for use in the state of California, meaning that they've done some testing at a state-certified commercial fire lab, and the testing that they have done has been deemed acceptable for the time being. There isn't an approved standard way to evaluate these vents yet for ember and flame intrusion. That's being worked on now. But until that standard has been approved, the state has accepted them for use temporarily. And then another vent that is harder to find but is still out there is called Fire Guard, and it uses screening and a fuse link device that holds open a door. And when that fuse link activates, the door closes. So I think from your perspective, you need to think about how these might work under ember exposures separately from flame contact exposures. Because if the Vulcan vent, for example, works because the intumescent paint swells up. And intumescent paint is the paint that will swell up when it reaches a certain temperature. In this case, most of these kind of products, and this is no exception, will activate at 325 to 350 degrees Fahrenheit. So if it sees that kind of a temperature, which is typically a fire kind of a temperature, it'll swell up and close off the vent. If it stops embers by doing that, then you don't really care for that, because an ember can come at your house and the temperature won't be 350 degrees Fahrenheit. It would be something a lot cooler than that. Okay.
Are these vents?
These vents are all kind of vents. They are eave, gable end, foundation. Many of them have designs for a dormer type of vent, a through roof vent. They are not a ridge vent, but almost any other kind of vent on a house they can be.
So foundation vents have been approved as past the testing so far?
Yes, it's the design and size have been accepted. Approved, you can't use that word, because approved means
Accepted versus approved?
approved means there's an accepted standard to test to and they passed it. If there isn't an accepted standard test method, then they've been accepted for use until. And then once that standard has been approved, then the deal is, and the state accepts that standard, then these vents will have to retest to whatever the standard happens to be. This is another, so these vents, the Brand Guard, the Vulcan, the Fire Guard, these are passive. You don't need to do anything, they work. Or not work, they work. You don't need to do anything for them to work besides put them in. If the Vulcan vent activates, you have to maybe replace the vent. If the Fire Guard vent trips, you're going to have to reset it. But in order to make it work, you just need to put it in place and it'll do its job. Some devices are active, meaning you have to do something. This ember deflector is an example of that, where you have these doors that can close over certain kind of vents. And then you have to open them at the end of the, and it's like an evacuation thing. You would close them. They're working on an automatic switch that'll manually close with a series of pulleys, but or you can get the manual device on this thing called Ember Deflector. So this is just a picture of an attic. A lot of debris, bird's nests. There are fine fuels in attics, so there are things that embers can ignite. So this is just a comment on unvented designs. You don't have vents. You move the insulation layer from the ceiling to the roof line. You do away with vents. This is something that's easier to do in new construction. It's easier to do in temperate climates. It's harder to do in colder climates. But it is an option, and you end up with no vents. Depending on where you happen to be, the building official will be more or less likely to like it, and so therefore more or less likely to approve it. Okay, so this is Ed's question. So about you put finer mesh screen up, what happens? So I'm going to just do this as an exercise. You can think about how to do it on your own house. So back in the late 80s, I was doing mostly moisture-related research, and I did a study on the moisture content of wood framing members in crawl spaces. And this is a diagram of this very simple layout of the house that was a real house in Richmond. And it had every place was a red circle, there was a vent. So there was vents on 3 of the 4 sides. Theoretically, you should have vents on every side so you can have cross ventilation, but there were vents on 3 sides. Each vent was 5 inches by 12 inches opening. Okay. The code says for a crawl space, and it's a little bit different for an attic, but for a crawl space it says 1 square foot of vent area per every 150 square feet of floor area. And the same rule is going to apply for roof. For attics, it's just going to be 1 to 130, usually 1 square foot of vent per 300 square feet of a ceiling area, of horizontal area. So this house was 42 feet long and 19 feet wide. That's about 800 square feet of floor area. That means we would need roughly 5 1/3 square feet of vent area, of vent opening. And maybe we can pass these around, but the way that vents work, here's a 1/4 inch mesh screen, here's an 1/8 of an inch mesh screen. So you're going to see that the wire to wire, in both cases, the vent takes up space. And so the deal here is you have to subtract out the part of the opening that is taken up by wire. And when you're looking for this 5 1/3 square feet, you want wide open. It's called net-free area. So no wire there area. So 1/8 of an inch takes up more space than 1/4 of an inch. The other thing that you're going to notice is that 1/8 of an inch, the finer the mesh screen, the finer the wire. Okay, so that's sort of a good thing. If you use the same wire diameter, then finer mesh, you would end up with less net free. Okay, so you got that handled. And so 1/16 of an inch mesh, finer wire diameter yet. Okay. So this is indeed what happens. If you want this kind of information, just let me know. I have a business card here you can pick up, and I can send you this little spreadsheet. But you'll notice, and so 4 mesh means 4 wires per inch. So 4 is the same as 1/4 inch mesh. 8 is the same as 1/8 of an inch, and 1/16 is the same as 1/16 of an inch, 1/16. You notice that the wire diameter gets tinier. The distance between the opening distance between the edge of the wire to edge of wire changes. And you get, if you were to calculate this all out, you would get the percent of the opening that you get in terms of net free as a function of mesh size and that related wire diameter. So with quarter-inch mesh, 81% of that opening is no wire taking up that space. Eighth of an inch, so it's quarter of an inch, it was 81%. Eighth of an inch, it's roughly 75%. And then 16th inch mesh, it's roughly 70.5%. And that gives you a net free area. If you take 81% times the total opening, which was 5 1/3 square feet, you can get how much you have. So you notice that in this house, you didn't meet the code requirement ever. And then you can make a nice graph. This is what you need to be, this upper dotted red dashed line. If you were at code, 1 square foot of net free area per 150 square feet of floor area, you'd be right at 5 a little more than 5 1/3, and you're a little bit less than that with the net opening, no mesh, no screen at all. And with quarter-inch mesh, you're a little bit less than that, and then you sort of dangle off. So you notice that you don't really lose a whole lot, but in this case, you'd never met. So what building officials might do, and what you can calculate, because you actually, if you're building a new house, they're going to care about this. If you do this as a retrofit, they may care, but they may not know. You would just have to bump up the number of vents in order to get the total amount of net free area to meet code. This lower thing here, this lower dotted line, was the impetus for that research project back in the late 80s that we have been talking about here. If you have a crawl space and you lay down plastic, then you can get away with less vent area. And you can go from 1 square foot per 150 to 1 square foot per 1,500 square feet. So you met that in every case if you had laid down plastic. And as a ground cover, that minimizes the amount of humidity getting into the air, moisture getting into the air, and therefore you have not the same moisture content problem potential with the wood framing. Any questions on this? You want the spreadsheet? Take my card and send me an email. You want help with the calculation? Send me an email. Okay. There's been a number of studies on the performance of windows. With a window, there's two things. There's the frame that the window is made of, and then there's the glass in the window. And the ways that a window could fail would be that the frame ignites and burns through, which is what we're seeing here. The frame deforms, allows the glass to fall out without the glass breaking, but it doesn't burn through necessarily, the frame, or that the glass breaks and then embers and flame enter. So the kind of exposures that might cause glass to break could be a radiant exposure from a large bush near but not touching the house. Your neighbor, if your neighbor happens to be close and that neighbor's house burns, ignites, then that would be a long exposure. And depending on how close the house is, you could have a radiant exposure enough to cause the glass to break. And then once the glass breaks, either flame enters or embers enter and ignite things inside. So this is how glass breaks in a window. If you think of the green part here as the frame material, and thus the red dashed line as the glass part of the window, and then there's some sort of heat exposure out, beyond the window. The temperature difference between the exposed glass, the part of the glass you look through, and the protected glass, the part of the glass that is protected by the frame, that temperature difference results in differential stresses, and it can cause, with enough temperature difference between the exposed and protected, it causes cracks that are already at the edge of the glass to propagate inward. Enough of these cracks propagating inward, and the glass breaks and falls out. Okay, so that's how it breaks. A lot of studies have shown that the most important part of your window is the glass. To the point where, with sort of one rare exception, you could be indifferent to frame type, buy windows based on glass. And so in that regard, dual pane is the way to go. And this is one place where energy efficiency and fire things align. You want dual pane at a minimum for energy purposes, and dual pane is better than single pane by a stretch from a fire perspective. Similarly, if you go to tempered glass, it's a lot better than annealed glass from a fire performance perspective. So this is just an example of a firewood pile that was ignited during a fire, and it was this radiant exposure from this fire that caused the damage that we see on this house. Some windows were broken, some windows were just damaged, but it was largely radiant exposure that did this. And this is what you can expect, even if the window doesn't fail in terms of glass breaking. Certain windows, and this is a vinyl window again, would have a propensity to sag with a radiant exposure, even though the glass won't break. So this would probably require replacement, and I'm sure the insurance company would replace this window. So from a no damage perspective, you can expect this kind depending on the radiant exposure that particular side of the house sees. Okay, we're good. Decks. So what kind of exposures can you expect decks to see? Embers, right. And depending on where the deck is and what you've done to your deck, flame from underneath, okay? So this is a test that evaluates things on top of the deck burning. And here we're talking exactly that. So here's a small deck at the top of a slope. This is a wood plastic composite decking product, window right next to the deck, and then brick siding next to that. So the non-combustible siding, no particular problem. I think if decks burned, fell off, and did no other damage, we would be concerned about the deck, but not nearly as concerned as we are, because right next to decks are often windows, sliding glass doors, and if the deck ignites, then it's easy for the fire to get into the house because the flame will then impinge on the glass, break it probably, and enter the house. So the things that we need to worry about then with regard to decks and other parts of your house that we talked about in terms of this exposure business is the likelihood of fire getting there to have an underdeck exposure, and then embers landing on top of the deck, and what might be on the deck to ignite. And then also there's the combustibility of the decking product itself. Okay, so here's looking down from that deck. Not very good defensible space. You could, take care of this to help your underdeck flame impingement potential. This is a place where you might want to consider, a retaining wall of some kind here to protect if it does ignite, particularly if you have no particular control over what happens down here. It's not your property, not cooperative neighbor, whatever. If this is your underdeck area, then this is a lot of debris stored under the deck. If it ignites, you have an exposure that is, pretty severe, and so any kind of combustible product isn't going to bode well in this kind of exposure. If you have this kind of storage issue with your deck and you really have no intention of changing it, then and only then you might want to consider enclosing the deck. If you enclose the deck and you have an open deck board kind of a deck, deck board with gaps where water can go through, and you're in let's back up and say you're in a place where it rains some, then you don't want the deck to develop rot problems because you don't get rid of the water that's going to accumulate in that underdeck area. So if you're going to enclose a deck vertically in this case, you want to make sure that you've taken care of the moisture issues that will develop over time. And then you want to make sure you're using a material that's going to resist the kind of exposure you're anticipating. So, okay, so here's an example of a solid surface deck, a non-combustible product. So this would be, no particular problem. In this case, it would be what's stored, what do you have on top of the deck that's combustible? Patio furniture, wood piles next to your sliding glass door, those kind of things. Brooms hanging on a nail. Those things can ignite and can become a problem even with a non-combustible deck. And finally, we can talk about the decking itself if you have a combustible decking product. So here, we can say that all combustible decking products are not equal. You have a way to differentiate to some degree how combustible a particular combustible decking product is. And one way is to just look at what's in this WUI product handbook, because it does provide some discrimination against, in particular, the products that are very flammable or very combustible versus those that aren't. And the way you do this is that this has a minimum heat release rate requirement to be approved for use. And this is an example of that. So we have two, on the right-hand side, we have two so-called Chapter 7A compliant decking products. And on the left, we have a product that isn't compliant with Chapter 7A. So the far right one is a redwood deck, and the middle one is a wood plastic composite that complies, and the far left one is a wood plastic composite that does not comply. So the other thing to really think about is maintaining decks in terms of eliminating fine debris that will accumulate at the wall to deck area that we see here, and then at the deck board to joist crossings. You have a lot of potential for debris to accumulate here, and if embers land there, then you'll have some ignition and potential for the fire to grow larger. Okay, siding. We talked a little bit about the standard way to test siding, combustible siding, that might be incorporated into the product acceptance book that the State Fire Marshal's Office publishes. And as I said, it is concerned about burn through and back of the siding into the stud cavity, and only that. It doesn't really evaluate flame spread up the wall at all. And so, this is just something to consider. And what research has shown in terms of the resistance to the penetration at a lap joint is all about the kind of lap joint. So let's see. We have a couple of examples here. So this is a shiplap joint, and the shiplap joint is one, and a tongue and groove would be similar. You don't have a bump out as you might in a bevel joint at the lap, and so the more complicated joints like a tongue and groove or a shiplap resist penetration at the joint more than a plain bevel joint when you're talking about combustible siding. This plain bevel joint is in a fiber cement product, and that same vulnerability doesn't apply here. It's something regarding the combustibility of the lap joint and the ability for the fire to communicate between the laps in a combustible product that makes the plain bevel joint vulnerable in a combustible siding product. The same thing doesn't apply. It doesn't work the same way with non-combustible fiber cement products. The penetration at the lap joint isn't really an issue with under normal exposures, at least, with a non-combustible product. Okay, so this is a demo again that I did, and it shows a combustible siding product and a non-combustible fiber cement product. Each one of them had a Class A brand at the base of the wall at the beginning of the test. And here is a pretty large vertical flame spread in the combustible siding product and none at all in the non-combustible. So the issue with vertical flame spread up the wall is even if you don't penetrate at a lap joint, you probably sooner or later will have a window in the way or an eave or a vent in the way. And so vertical flame spread is an issue because of the things that it will eventually see. So here is a wood siding product that has met, it's a fiber retardant treated exterior rated wood siding product that has met the ignition resistant criteria. And here is non-combustible. And we're going to just look at this over time. Again, it's an A brand at the bottom. As it turns out, this particular product has a plain bevel joint also, but because of the intumescent coating nature, the intumescent quality in this particular fire retardant treated product, that joint isn't as vulnerable either as it would be in a flat out combustible siding product. So this is just an example on the left. This is a fiber cement siding product and a combustible trim product. This is a reentrant or interior corner where you often find vegetation. If you're going to go through the trouble of having a non-combustible siding product, make sure that the trim gives you comparable performance, because otherwise it'll be the weak link. Okay, so coatings. There's a couple of things with regard to coatings that I want to cover, and then anything else you want to cover. One is things you might do to your deck that aren't intended to provide any fire resistance, and whether or not it makes it worse from a fire perspective. These would be like stains you might apply because you like the look of a stained deck, or you want to extend the life of the deck and you like the way that the stains do that. One is to describe this process to get exterior rated fire retardant materials, and then other kind of coatings, and then gels. I want to talk a little bit about gel coatings. Okay. There is a durable spray or brush-on treatment that will make my wood shake roof fire resistant. I answered false. So let's talk about that. And I think part of it is there is a durable spray or brush-on treatment that will make my wood shake roof fire resistant. And I think the key word there is durable. And when I use the word durable, maybe we should have talked about what durable means. Definitely, there are treatments that you can apply to your roof that will improve the fire performance and make it more fire resistant tomorrow, probably even next week. But with some weathering, at some rate, it's going to lose its effectiveness, and you're not going to know when. So that's the general problem today with most with most topically applied products used in exterior exposures. They don't weather well, and the chemistry hasn't been worked out yet to make the service life predictable. So in the short term, until these things are worked out, they definitely work in the short term. You don't know how long that term is. So this is a treatment retort, and this is how materials that get wood materials that get the ignition resistant classification are treated. So they get put into this cylinder. This is wood shingles. They get put into the cylinder, the door's closed, the chemical is injected, and then under a vacuum and then pressure impregnation process, the chemicals get get injected into the wood, And then there's another step, a drying step that polymerizes these things and makes and in effect fixes them in the wood. So and then they in California, anything that's going to be on the roof has to pass a natural weathering cycle and pass the test before it can be sold. And if it's used as a sidewall or a decking material and has this ignition-resistant material, classification has to undergo a prescribed accelerated weathering test and then pass the fire test. So there's something. Maybe you can say that it's not the right weathering test, but it's something that you can, compare by anyway. Okay, so this is how you get both the roof shake that has the standalone Class B rating and the ignition-resistant material undergo the same process. The amount of chemical may change, but the steps are generally the same. Okay, now let's look at this. This is I put a stain on my deck because I like the way it looks, and I think it's going to help me have a more durable deck. But I don't want it to degrade the fire performance of it. Will it? And so I did a couple of these kind of tests in some demonstrations. And the day before the fire demonstration, I put an oil-based stain on, in this case, a left-hand deck, and the right-hand deck. These are both redwood decks that had been aging for more than a year, just sitting outside. So I put them both in a drying oven and dried them for a couple of days, and then I put the stain on the night before the test. Drove to the test site and then put two, again, Class B brands on each deck. This is sort of during the test, and then this is after. So this is sort of observational. I didn't measure anything in particular, but they look about the same. What happened was that the stain deck burned more rapidly for a short while, but they both went out at about the same time, and the burn pattern was very similar for the stained versus unstained. The stain is going to be going away over time, so the worst case I felt was igniting the day after, right away, so to speak. It's not going to get any worse than this, and to me indicated that there really isn't much impact of that stain. So I don't think you should rely on a coating to give you fire performance, and you shouldn't be worried about it if you have it to detract from how it might perform. So here's an example of a gel product. So this is a corner section. Often, as you've noticed, I also often use corner sections in these fire demonstrations. The siding is exactly the same. It's a nominal 4-inch wood, end-glued redwood siding pattern that has a rabbited bevel siding pattern joint. The left-hand panel had a gel applied by the distributor, and then plastic wrap covered the non-applied side so that no gel hit it. And then we did this sort of early on, and a few hours later, we did this test that you're going to see. So in order to do the test, the plastic came off, and then a burning one of these brands went at the base of each wall. So here we are sort of during it. Class B brand, gel-coated wall, non-gel-coated wall. Okay, this is sort of at the end of it. So definitely the non-gel-coated wall, the burn was, the vertical flame spread was a lot greater. It went all the way up the wall. It's still burning actually right now. The gel wall is out. There's a hole at the base of the wall next to where the thing was burning for the non-gel wall, and the same thing is happening with the gel wall. So it definitely performed better than not, but did it do what you wanted it to do, which was not burn through? And the thing that I noticed in this was, if you notice at this drip edges are hard to get anyway. And depending on how close you are, you can have an easier or harder time, but they missed that part of the drip edge, so it was not protected. And it was sort of low enough down that this could have been it. And down is hard to get to, but down is where you need to get. So this is one of the vulnerabilities. So I think personally, you can see that they perform better than not, but they don't necessarily perform the way you want it to perform. And if you had done clearance or careful management around near your home, you may have the same kind of impact or effect. Thank you so much. I appreciate you hanging with me and for doing my clicker experiment.